Hi guys, welcome back to Calculus with Mr. Robeson. Today we are going to look at our next section on limits, so taking limits and limits of continuous functions. Alright, so we briefly mentioned continuous in class the other day. Continuous means, well, we'll get into an actual definition later, but continuous means that you can draw it without having to pick up your pencil. So if you're going to draw the graph of the curve for the function f, like f of x is some sort of graph, you could draw that without having to pick up your pencil. So there's no holes, there's no jumps, there's no vertical asymptotes. So it's a nice smooth curve. So that means if we take the limit as x goes to some x value, say c, then the limit will always just be the function value. All right, so that is useful for taking limits in lots of ways. All right, so this is going to work for most functions. So most functions, you're just going to plug in their number, and that's what we're going to get for the limit. All right, so this works for constant functions, linear functions, polynomials, exponential functions. We'll see some other types of functions. It works for a lot of trig functions. It works for a lot of radical functions. All right, but most of the times in this class, we'll be more interested in times where this doesn't work, where something's not continuous, or where there's like a hole, or interesting cases. These are the boring cases, really. All right, so let's take a look at this guy here. So this first one, we want the limit as x goes to 2 of 4x squared plus 3. Well, 4x squared plus 3, that's a polynomial. It's quadratic. It's going to be a parabola. It's just going to be a nice U shape. It's going to look something, well, can't draw so well yet, but we're still practicing here. But it's going to look something like that. So this limit is just going to be what we get when we plug in 2. So we're just going to plug in 2. 4 times 2 squared plus 3. So that's 4 times 4 is 16. Plus 3 gives us 19. So this limit is just 19. All right, this next one, we want the limit as x goes to 0 of e to the 2x plus 1. All right, so this is an exponential function. So its graph would look something like this. It would have a horizontal asymptote, and then it would shoot up real quick. Like that. All right, so if we just plug in 0, we get e to the 2 times 0 is 0, plus 1. Anything to the 0 power is 1, so 1 plus 1, and it just gives us 2. So our limit here is 2. All right, so now you're supposed to try one here. So we want the limit as x goes to negative 2 of 3x minus 7 inside the absolute value bars. Remember, absolute value bars make everything positive in the end. All right, so take a couple of seconds and see if you can work this out. All right, hopefully you've had some time to work it out. So it's a continuous function. Remember, absolute value, the graph of it is just going to be a v. It's just going to keep going in each direction. There's our v. All right, so we're just going to plug in negative 2. So we get the absolute value of 3 times negative 2 minus 7. Close our absolute value. 3 times negative 2 is negative 6 minus 7. Still inside the absolute value, so we got negative 13. Still inside the absolute value. So the absolute value says the distance between negative 13 and 0 is just 13 units. So our answer here is 13. Hopefully you got 13. All right, next up. So we don't actually need to even have what the functions are as long as we know that they are continuous. So suppose f and g are continuous functions and the following are true. So as we go to 1 in f, we get 3. As we go to 1 in g, we get 5. As we go to 3 in g, we get negative 2. And as we go to 5 in f, we get negative 1. All right, so the first one up here, we want the limit as x goes to 1 of f of x plus g of x. Well, we know we can split that. It's really just the limit as x goes to 1 in f of x plus the limit as x goes to 1 in g of x. So now we go over here and we say, oh, well, look, the limit as x goes to 1 of f of x, that's just 3. So this guy here is just 3. All right, the limit as x goes to 1 in g of x, that's the second one here. That's just 5. So really this problem is just 3 plus 5 is 8. So So our limit here is 8. All right, down here, we want the limit as x goes to 1 of f of g of x. So we have composite functions. Remember, sometimes we have this written like this, f of g of x. That's the same thing as this right here. Just review. All right, so what we can do is we can bring the limit inside. So this is f of the limit as x goes to 1 of g of x. And we know the limit as x goes to 1 of g of x. It's over here. It is 5. So we get that this is f of 5. All right, now, we don't necessarily know that f of 5 is negative 1. We know the limit as x goes to 5 of f of x is negative 1. But since they are continuous functions, that tells us that if the limit equals negative 1 in f as x goes to 5, then that means f of 5 is also equal to negative 1. It doesn't actually have a hole there or anything like that. Its function value is the same as that limit value. So it gets us negative 1. Right? It doesn't always have to be the case. If it wasn't continuous, that wouldn't work. All right, next up, the limit as x goes to 1. So on top, we're going to 1 in f of x. We've done that a couple times. We get 3. So it looks like on top we are getting 3 minus 3. On the bottom, x is going to 1, but we got x plus 2 inside of the g of x. So we do x plus 2 first. So it'd be 1 plus 2 would be 3. So we got the limit basically as, that becomes the limit as x goes to 3 of g of x down on the bottom. And if we look over here, let's see, that is negative 2. All right, so 3 minus 3 is 0 over negative 2. 0 on the top of a fraction gives us 0, so that limit is just 0. All right, a couple more, so we can make our functions look a little more complicated. So radical functions, as long as we are in the domain, we can use direct substitution. We can just plug in, and that's what we've been doing, direct substitution, just plugging in the number. All right, same with rational functions. As long as the bottom doesn't equal 0, so as long as this part here isn't going to 0, we can pretty much always just plug into these guys. All right, so for the first one, we want y to go to 1. Again, I switch letters on you. It doesn't change anything. So we get the square root of 4 minus 1 squared, which is the square root of 4 minus 1, or just the square root of 3. We don't have to simplify that. We can just leave it as the square root of 3. If we were to change it to a decimal, we need 3 decimal places in this class, guys. Next, the limit as x goes to 1. In this guy, well, let's just plug in 1 and see what happens. So we get 1 squared plus 2 times 1 is 2, plus 1 at the end there, over 1 plus 1. So 1 plus 2 plus 1 is 4. 1 plus 1 is 2. And we just get that our limit here is 2. All right, last one. You guys give this one a try. We want the limit as x goes to 3 of the cubed root, so this little guy out here means the third root, of 2x squared minus 10. All right, if you need more time, just go ahead and pause the video and keep working. I'm going to work it out just to save a little time for the rest of us. So this is a continuous function. As long as 3 is in the domain, we can plug in here. And since it's a cube root, we don't have any domain issues. The odd roots are no problems. We can take odd roots of negative numbers. Can't do it with the even roots, though. All right, so we're just plugging in. So we got the cubed root of 2 times 3 squared minus 10. So 3 squared is 9. 9 times 2 is 18. We get 18 minus 10 in there, so we get 8. So we get the cubed root of 8. And then we want to know what power what number to the third power gives us 8. Well, that's actually 2. So 2 to the third power gives us 8. So that means the cubed root of 8 gives us back 2. So our answer here is 2. All right, so that was some basics of limits. So limits when we were working with continuous functions. Next class, we'll look at a little more complicated limits. Okay, so we'll get a little more complicated next class with our limits. All right, see you.